So, let us discuss now how errors actually propagate, or rather it reduces as we take on an iterative method. It could actually increase or decrease depending on certain situation, that also we will see. So, let us say that we talk about error estimates in an iterative method. And we give a very simple example. So, most of the mathematical functions that we come across can be expanded in terms of an infinite series. Say for example, we take this function exponential x, which can be written as 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So, as we take successive terms in this expansion, the value of exponential x gets better and better, and it can only become exact when we take all terms up to infinity into consideration. But since that is not possible in a numeric method, we will have to truncate this series after a certain number of terms, and your approximation or these approximation of truncating beyond a certain or rather before a certain number of terms or by a certain number of terms will make sense if the error associated with it is small and can be ignored. Let us see an example. So, we want to calculate a particular value of x, say we want to calculate what is exponential 0.5. So, that is you have x equal to 0.5. Okay. Now, of course, we know that if we take just the first term, that is like missing out a large number of terms, and we get exponential of 0.5 equal to 1, which is not a good approximation. So, of course, our starting point would be x equal to exponential x equal to 1, and so 0.5 is equal to 1, and then we add successive terms such as x, which is 0.5, and x square by 2 factorial, which is 0.5 square by 2 factorial, and so on. And then we try to see that how we converge and when we converge. Now, the convergence will depend upon a pre-decided error, that is, if our successive approximation gets us below a certain error, we will stop there. That is the idea behind it. So, let us just the exact value is, you can use your calculator to know that exact value. The exact value is exponential 0.5, it is equal to 1.64871 and so on. Okay. So, that is the exact value, and of course, we are starting with a value which is very less, which is equal to 1, that is the first term in that expression, and we will successively add x and see what the error is compared to the exact value, and we will also define a quantity called as the approximate relative error, and we will want this approximate relative error to go below a certain threshold value, which will be decided by us, that is by you. So, in order to do that, let us look into this, that pre-decided condition we shall stop when an approximate relative error, let me define it, approximate relative error in error goes below certain number, goes below epsilon 0, take epsilon 0 to be equal to 0.05%. Okay. That is a good enough approximation, and we decide that we will stop there. If you do not think that this is a good approximation, you can go even below that, but it does not matter, it will take more steps into your calculation, but at this moment let us stick to this, that will stop if successively computing this value of exponential 0.5, if we get to a point that our error is actually lower than this, then we will stop our iteration and we will say that this is the value that we get. So, what is so this is, let us call this quantity as epsilon A. So, epsilon A is defined as the current approximation and minus the previous approximation divided by the current approximation. And multiply it by 100 in order to get it in percent. So, that is my approximate relative error, and it is also in expressed in percentage. So, if this epsilon A goes below or equal to epsilon 0, then we shall stop iteration, which means including successive terms, and settle with the value of exponential 0.5. So, let us see how this happens. Let us look at exponential x as 1 plus x. That is the first term that we are going to add, and then it becomes, because x equal to 0.5, then it becomes equal to 1.5. So, how far are we? So, we have these or let us say now we talk about also about the truncation error or whatever, the exact value minus the approximate value. So, that we have defined in earlier as well. So, 1 for this is the exact value minus this approximate value divided by the exact value into percent. So, this becomes equal to, if you calculate it, it becomes equal to 9.02%. But even more serious error is caused at this approximation level, where this level of approximation yields 1.5, the other one yields 1. So, divided by the current approximation into 100, that gives us a value which is 33.3%. So, this value 1.5 is way off compared to 1.64, and we cannot stop here. So, now include x square by 2 factorial, which is so this is 0.5 square by 2, which is equal to 0.25 divided by 2, which is equal to 0.125, and if we actually include it, then it becomes exponential 0.5 at this level becomes equal to 1 plus 0.5 plus 0.125, and this becomes equal to 1.625. We are still away, and we can calculate the epsilon t, which is the error, the percentage relative error, and also the approximate relative error, and these can be calculated in percent, and then so calculate epsilon t and epsilon a, then of course go to x cube by 3 factorial, which is nothing but 0.5 whole cube by its 6, and then you add it to this term. So, this becomes, this gives a exponential 0.5 equal to 1 plus 0.5 plus 0.125 plus this quantity. I am not calculating it, but you can use your calculator and can do it. So, at this level it is this, and then again calculate epsilon t and epsilon a, check whether epsilon a falls below 0.05%, and if it does, then you are done. Okay. So, let us make a table out of it, and we will say that this is the terms, this is the result, that is what we get out of these. So, it is basically result for exponential 0.5 by adding successive terms, and then we have the relative error in percent, and this is that approximate error in percent. Okay. So, remember this epsilon t, epsilon actually stands for error, just a convention. This is taken with respect to the exact value. Now, because we know the exact value here by a trivial computation using either a computer or just even a calculator would do, that is why we are calculating this. But if this is not available, that is you do not know the exact value, then of course, the only thing that is important for us is this approximate relative error, which calculates the error as it propagates, or rather as it goes down in taking into account various terms. Okay. So, we are actually talking about errors going down if we take more and more terms into these infinites of these infinite series into consideration. All right. So, your 1, if this is equal to 1 and this is 39.3%, you can check that, which is 1.648, that number 648721 minus 1 divided by 1.648721 into percent. So, that comes to about 40%, and of course, there is no approximate error in this particular step, because we are just starting this. That is the first step. And when you go to the second step, then the result is 1.5. We have already computed that this is 9.03, and we have already computed that this is 33.3. Okay. So, you see the error has come down by including just one term from 39% to about 9%. In the third iteration, when you also include a x square by 2 factorial, which is the third term, and one gets a 1.625, which is what we have seen. We have not calculated it, but you do it. I suggest that you do it, and this comes down drastically to 7.69%. And the 4, that is equal to your 1.6458 and 33333, and this is only 0.175%, and this is 1.27%. Similarly, in the fifth iteration, one gets a 1.6484 37500, and one gets it as 0.0172, and one gets it less than 1% error, which is 0.158. We still are above that 0.05%, but maybe one more step could take care of it, and it does. In fact, it gives you 648 697 917, and this is 0.00142, and this is really 0.0158. So, you see that it falls below 0.05%, and we can stop the iteration, One, of course, good thing to ask, that how the error converges in how many steps the error would converge to a desired value, and in that case you need to know the analytic form of the convergence, and that also can be found. We will see an example soon. So, now this is the value, this is the result, is this is the final value that we take as, and if you think about it, our exact value was 1.648721. So, okay, so that's fairly close. It's 8697 if you take, so it's 1.6487 instead of 869 and so on. So, this is the exact value, and we get within only 6 iterations this has converged to a value that is desirable in this particular context. Okay. So, this is, the just 2 examples that we have considered. In the first example, in the rail track problem, we have considered how taking a slightly lesser or rather very approximate expression for calculating where the rail track would be joined gave me a result which is way off than a certain slightly better approximation. And here you see that in an infinite series, as we keep adding the terms in the infinite series, you have these convergence of these values to the exact values very fast. In fact, if you go to one more step, you will probably get a value which is very close. Okay. So, that is because already we are at the approximate error to have a value less than 0.05%. In fact, it is 0.01%, just about that. So, we will continue with this error as and when with every method that we actually learn, and it is very important for us to know that how the errors propagate, what is the analytic form of the error, and how they are going to affect our our calculations or rather our predictions of the physical things that we are trying to. So, let us now go to a topic, a particular topic of discussion, which we are all familiar to right from our mid school days, which are about solving equations. I mean, these equations are there everywhere. We have learned Newton's laws of motion or Newton's second law very early in our career, and we know that it is a second order linear differential equation in the absence of any damping term, and we need to solve it. And sometimes these equations are differential equations, sometimes these equations are simply algebraic equations with just one unknown, and sometimes there are more complicated equations which are systems of equations with more than one unknown and sometimes large number of unknowns. And analytically it becomes a problem to solve anything with more than 2 or 3 unknowns, and even sometimes 3 unknowns become a problem unless we are given another condition in some physical situations that may arise. And we are interested in talking about solutions of equations, but these equations are mostly nonlinear equations. Linear equations, I believe that these are easier to solve. Nonlinear equations are more difficult, and sometimes the nonlinearity is quite complicated and we need to get to the fact that we have to sometimes solve nonlinear equations, and those nonlinear equations, there should be some numerical methods to solve those nonlinear equations. So, any equation is cast in the form f of x equal to 0. Okay. Okay, I mean that is the we need to solve, say this is a nonlinear equation and we need the roots of that. So, take an example that let us say one has to solve a f x equal to a minus 1 over x, which is equal to 0 for a to be greater than 0. Okay. Very simple equation, you do not, one does not really need a numerical method to do that. X is equal to 1 over a is the solution, everybody knows. But suppose it is not a simple equation as simple as this, but it is a complicated equation. But can we talk about a generic method or a general method in order to address such a complicated, more complicated nonlinear equation? Let us see that. So, of course, if I plot this thing, it will look like, so this is f of x as a function of x, and if I do it, it looks like this, and it has a crossing at, let us show it by a different color, at 1 over a. So, at 1 over a there is a point, the crossing point, and say this is 2 over a and things like that, and then of course, that is there. And but we do not know the solution of this, that is the assumption. Of course, we know here, but let us assume that we do not know the solution. And if we do not know the solution, let us take a solution, let us assume that x equal to x 0 is the solution, which means I do not know exactly where it is, but I assume that it is somewhere here is the solution. I just guessed it, okay? Nobody told me, it could be a wild guess. I could have guessed it somewhere far away on the x axis, but then I would have, there are problems with that, which we are going to see in a while. But say we have somehow guessed it approximately correct, and it is not too far away from 1 over a, and this x 0 lies in the somewhere in the vicinity of that. Okay. Now, what we do is that we take this point, which is called a point x 0 f x 0, that is the x y point, and draw a tangent at this point. I have to be careful. It is not touching. So, let me, I want to draw a tangent at this point. Let me just draw both the curves a little better. Okay, so I have this curve which is like this, and my at x 0 I want to draw a tangent. Okay, I did a tangent. Okay, approximately take that as a tangent. Slightly harder to draw on this board, but that is the tangent. So, I drew a tangent at this point. So, this is step number 1, this is step number 2, that assume a tangent drawn at x 0 and f x 0, which cuts the x axis at x equal to x 1. So, x 1, let me write it with a different color. This x 1, this point x 1, which is this point. Okay. So, this point x 1 is my new root of this equation f x equal to a minus 1 over x, and which is a better approximation than the x 0 that I have originally assumed. Now, you could say that I could have assumed a very wrong point where the tangent cannot be drawn, or the function has you cannot either draw a tangent there or there is something that is wrong with this, and we could actually go away from x 0. So, x 0 could have been a better estimate than x 1, that could happen, I am not denying the fact. So, there are certain conditions which you have to obey or which you have to follow in order to find or guess a root of this equation in a slightly intelligent manner. All right. So, this is the situation. So, we have drawn this and we have got a point x 1 which is the solution. Okay. So, x 1 is an improved approximation for the root. Okay. Now, number 3, we want to obtain an equation for x 1 such that solving it I get a value of x 1 and in terms of x 0 which is your original guess, and if we can form an induction or rather by induction if we can say that the same equation is actually the same equation also describes the x 2 starting from a value x 1 which was our previous guess. So, if that is possible, then of course, you form an iterative equation which successively one solves and one gets a x 1, x 2, x 3, x 4 and successively you make the root better and better. So, in order to do this, match the slopes obtained from the tangent line and the derivative of f x at x 0. Okay. I mean they are same. So, I am just matching them or rather equating them. So, the derivative at x or x 0 is calculated using f prime of x equal to f of x 0 minus f of x 1 is just a 2-point derivative which we will learn in a more detailed manner as the course progresses. And so, this is a 2-point method by which we take the derivative between two neighboring points, calculate the value of the function at the neighboring points and take the difference between the 2 points and f of x 0 minus 0 because f of x 1 is equal to 0. If you see the function actually has a value 0 at x 1 equal to 0 because it touches the the x axis, and this is nothing but x 0 minus x 1, correct. So, this is fine. Now, I just do a cross multiplication of this. So, it is a x 0 minus x 1 f prime of x, this is equal to f of x 0. Okay. Now, you see from because my because I have f of x equal to a minus 1 over x, I can calculate f prime of x is equal to 1 over x square. And what is my f of x 0? Also f of x 0 is equal to a minus 1 over x 0. So, these are the two things that are there. So, I am just going to put them. Just before that, let us finish one more step. So, it is f of x 0 divided by f prime of x, and this gives me x 1 equal to x 0 minus f of x naught, and so this is this is actually a calculate, this is the thing is calculated, the slope is calculated at x equal to x naught. So, this is actually x naught and this is also at x naught. So, this is x naught. So, this is x naught and so on. So, this is f prime of x naught and this is nothing but so we got a relationship for x 1 in terms of x 0 and remember this is what is wanted or rather this is what was desirable to begin with, that we get the value of this new root and find a relationship with it, the old root, and the old root in this case is a starting value. So, my x equal or rather x 1 equal to a minus 1 by x 0 divided by 1 by x 0 square. So, this is f of x 0, the numerator is f of x 0 and then it is f prime of x 0 and so this is there is a x 0 that is missing and it is this. Okay. And if you simplify this, this becomes equal to x 0 minus x 0 square a by 1 minus x 0 and this is equal to x 0 minus a x 0 square plus x 0 and this if you simplify then it becomes x 1 becomes equal to x 0 2 minus a x 0. So, this of course gives me an equation of x 1 in terms of x 0, okay. And this is something that is is important for us. Let us see this carefully. So, a general iteration method can be used because we have started with only a pair of values of x 1 and x 0. So, we can take it rather continue it for any x n plus 1 and x n and so this is x n plus 1 which is the new approximate root minus 2 minus a into the old root and for n of course greater than equal to 0. Use a slight change in variable, then we have if we write r n, this is equal to 1 minus a x n, then we can write x n plus 1 equal to x n 1 plus 1 minus a x n and this is nothing but r n. So, this is equal to x n 1 plus r n and the error is in this case is equal to epsilon n, let us call it epsilon n at the nth level, which is equal to 1 over a minus x to the power n. At the nth level, this is the exact root, we are not talking about the relative one as yet, it is just the just the bare error, which is the exact value minus the approximate value at the nth iteration. Now, if that is true, then this is nothing but equal to r n divided by a. See, the r n has a definition. So, this gives you r n by a, r n by a equal to 1 over a minus x n, and since we have 1 over a minus x n here. So, this is equal to r n over a. So, that is the error at the nth level. And now, we want to check the convergence of this method. So, the convergence of this method is can be tested as follows. So, it is a r n plus 1 which is equal to 1 minus a x n plus 1, and this is the definition of Rn because we started from Rn equal to 1 minus Axn. So, Rn plus 1 is equal to 1 minus Axn plus 1. And if you look at the definition of Axn, just Xn plus 1 here, this is the definition Xn plus 1, it is equal to Xn 1 plus Rn. And so, we can write this as 1 minus Axn 1 plus Rn, and this is nothing but equal to 1 minus 1 Rn and 1 plus Rn, because Axn is nothing but 1 minus Rn. So, that gives, if you simplify this, basically what you need to do is that you just open the bracket. So, this is equal to plus it is a plus Rn square. So, this will cancel. So, what I get is that Rn plus 1 is equal to Rn square. So, this is an important thing result that we have, that using induction again one can get Rn equal to R0 to the power 2n. Okay. So, if you put n equal to 0, then I get R1 as R0 square, and then for R2 putting n equal to 2, I will get R3 equal to R2 square, but R2 is nothing but R1 square. So, you gather a square at every stage. So, at the nth stage you gather a factor of 2n in the power, and this is your the Rn this thing, and of course, as I said earlier that n is greater than equal to 0. So, this E n goes to 0 as Rn converges to 0, 0 as n tends to infinity. Remember, what is the relation? The relation is that your epsilon n is nothing but Rn by A, and A is greater than 0. So, Rn epsilon n will go to 0 if Rn goes to 0 as n goes to infinity. It should not grow, it should die down. So, for that to happen, so for Rn to converge, we need R0 less than 1. Okay. So, the mod of R0 should be less than 1. So, that is how it has to be chosen. Let us go through one more step and then it will be clearer to you. So, a minus 1 less than 1 minus Ax0 less than 1. So, you see this R0, because the definition of R0 is 1 minus Ax0. So, 1 minus Ax0 should lie between a minus 1 and plus 1 for the convergence to occur. So, this of course gives the condition that 0 is less than x0 is less than 2 minus 2 by A. So, in this particular situation, let us go back to this original figure. If your x0 does not satisfy that condition, that is between 0 and 0 is here, okay, and 2 by A, that is why we have plotted 2 by A, then you have no chance of converging. Does not matter how many steps you follow in this iterative scheme to reach closer and closer to the exact solution. Okay. So, that is the condition, and we said that it is not any value that would do it, you have to have an intelligent value, and the value comes out that it should be between 0 and 2 by A, which is shown in that plot that I just showed you. Thus, Xn converges to 1 over A. It is necessary to choose x0 in constrained by this, or rather in this fashion, whatever you want to write. Okay. So, that is the condition for one to have a convergence and so on. And let us see the nature of convergence. This is what I was saying earlier, that we need to understand that how the convergence happens. So, let us talk about the let us say pace or speed of convergence. So, for the error at the nth step, E n plus 1 equal to R n plus by n plus 1 by a, which is nothing but R n square by a, which is equal to E n square a square by a. So, that is the convergence, that is epsilon, the error at the n plus 1th level varies as a square of the error at the nth level. So, of course, if epsilon n is small, in successive steps it gets smaller and smaller, and this is what we have seen in that last problem that we did. Thus, epsilon n plus 1 is simply a epsilon n square. This is the convergence, and in any iterative method we should test the convergence. So, we can simply write this as epsilon n plus 1, it does not matter, of course, I mean it is 1 over a, this is equal to a square epsilon n square, which is equal to epsilon n square divided by 1 by a square, and so on. Okay. So, what I am trying to say is that the epsilon n converges to 0 quadratically, and that is the speed of convergence. If you want faster convergence, that is a power which is larger than 2, then there has to be different method in order to implement this and so on. In a root finding problem, usually we find that these are convergent in this particular fashion, that is a quadratic convergence. And quadratic convergence is good because if you are usually in normal nonlinear equations that we come across, the convergence is quite fast. In fact, one does not have to go to too many iterations in order to have convergence of this. So, thus we have, what we have done is that we have taken a problem of nonlinear equation. It, of course, the interpretation goes to you. I have taken a very simple equation, 1 over a equal to x, or 1 over f of x equal to 1 over a minus x equal to 0. That equation had to be solved, and what we did is that we have taken a guess value x 0, calculated the slope of the value at the x 0 f x 0, that is x y point, and extended that tangent to meet the x axis, so that we know the new position of the new root, and then we have found out in induction formula that how we can actually iterate the root from one approximation or one iteration step to another, and this is how we have gone ahead and converged. The convergence comes out to be a quadratic convergence. Okay. So, we will see some examples related to that.